Okay, so one of you asked me to actually explain how LeChatelier's principle works, and so I'm going to try to do it as fast and easy as I can. I'm actually in my wood shop right now. I would show you a little video of what this looks like and what my conditions are for quarantine, but I'll send a video of that later if you want. But for LeChatelier's principle right here. So, and Lydia, thanks for putting that out there, that you guys need a little bit of help. We're only going to deal with just a few changes to the actual reaction, and when those changes are happening, what we're saying is what happens to the equilibrium as a result of those changes. So here are the different changes that can be placed on a reaction. So there are changes in concentration, changes in pressure, temperature, or adding a catalyst to the reaction and seeing what happens as a result. So what I have up here is a basic reaction. A plus B yields C plus D. It could be any chemical compounds as long as it's an equilibrium reaction. And I have drawn underneath this, if you can tell my terrible artistic abilities, is a bathtub. And so what I'm going to do is fill the bathtub with water, and we're going to say that the water acts as both the reactants and products being on each side of this bathtub. And so if I fill it with water, we're merely talking about concentration at first, but if I fill it with water, and then I take a scoop and I scoop some water out of one side of the bathtub like this, and I scoop out a perfect amount, the bathtub would look like this. Is that true? I can't hear you. So I would assume you'd say, no, that's not what happens. What happens is the water rushes this way to shift to accommodate for that stress, that removal of water. So what would happen in terms of a reaction is the reaction would shift this way, and actually instead of having additional products produced, you would actually have additional reactants produced. So it would shift back this way to produce more reactants. That would be relative to your KEQ expression, but we can get to that later. So it would shift back to make more reactants. Okay, I have some issues cleaning this, but we'll give it a shot. So what if instead of taking water out, I actually added water to it? So I'm drawing my water again. Here's my water. And I'm going to add water to it. So I've got a faucet on this side, right? And I put some water in here. It would make a giant pile of water. Yeah? Is that true? Of course not. What would happen is the water would rush this way. So in the same thing in the reaction up at the top, if I actually add more reactant to it, so I add more reactant, which way would it shift? Just like the bathtub example, it would shift to the right to form more products. So more C and D would be produced. That's the difference in the concentrations, okay? You can also do this in terms of gas molecules, and that would be where you manipulate pressure. You can certainly manipulate concentration or partial pressures of gas molecules, but if you change the pressure of the system, in other words, you make the volume smaller or you increase the number of particles, we still do the same thing as concentration, but if you change the size of it, it would shift similarly. You can't really use the bathtub to demonstrate that, but let me erase this if I can. Got some issues with the erasing on my board in here. But if I did this in terms of gas molecules, it would be very similar. So let's say that A and B this time are gases, and so are C and D. So if I said, interesting learning curve, if I said this was A plus B, and this is a gas, 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 I have 2 moles of gas on one side and 2 moles of gas on the other. So if I change the pressure, there's not going to be any change here because there's not more moles of gas on one side or the other. However, if I had, say, a 2 in front of this, so this is now balanced, and I say it produces 2 moles of C. There are actually 3 moles of gas on this side, and there are 2 moles, looking at the coefficients, of gas on the reactant side. So if I increase the pressure, so if this is the volume of the box that I have or the space that I have, and instead I increase the pressure so I make it smaller, it's going to shift to the side that has less gas molecules. So it actually shift back to produce more reactants. If instead I took a smaller space and I decreased the pressure, so I made it larger, this would be decreasing the pressure and making it more spread out, the molecules won't collide as often, then it would shift to the side that has more gas molecules. So up here it would shift to the side with more gas molecules. That is the effect of pressure on an equilibrium system. It doesn't do anything with aqueous molecules or solids or liquids. It only changes things with pressure. Let's see. Temperature. Temperature only affects things that have changes in heat associated with it. So endothermic or exothermic reactions. So again, with my erasing learning curve here, let's take this off real quickly. If I take this off, and I just look in terms of pressure, let's say I go back to my kind of 1-to-1 ratios here. If I say it's exothermic, so I said that the delta H for this reaction was negative 100 kilojoules, okay? That means that heat is leaving the system, so I would write my heat or 100 kilojoules as a product of the reaction, meaning that it's on that side. Well, if I increase the temperature, and I increase the temperature here, which way would it shift? Just like the bathtub, it would shift back this way. So if I increase my temperature, it will actually cause the reaction to shift back this way, producing more reactants. Now, if I were to set up a KEQ expression for this, and we did this in class, but I know you guys have slept many moons since then, it would be my product values divided by my reactant values. Oh, my pen's not doing well. Look at that. Ooh, wow, that's not good. I think it's the residue on here. Let me grab another pen. Yeah, that's not helping much either. Anyway, the reactants would be on the bottom. And so what would happen is if it increases this way, these would get larger. It's going to be relative to your K value. Your K value is never going to change, provided it changes in concentration or pressure. If you change the temperature though, and in this case we are changing the temperature, it would change my K value. Since I have a larger denominator and basically the same numerator, my KEQ is actually going to go down because the denominator is going to get larger. Whereas if this were exothermic and I decreased the heat, it would shift towards the right, making the concentrations of the products larger. The numerator would be larger. It would change my K value. This is the only time and only way that you can change your K is by changing temperature. The very last thing in LeChatelier's principle is a catalyst. A catalyst just makes the reaction go faster. It doesn't change the reaction at all. It doesn't cause it to shift one way or the other. What it does is it allows it to get to equilibrium more quickly. And if it gets there more quickly, then it's still at equilibrium. It does not change your K value. These values will all stay the same relative to one another. So changing temperature is the only way to change your K. Catalyst will not change your equilibrium at all. Pressure only affects gases, and concentrations would just be your bathtub. If you increase the concentration of reactants, it will shift back to form more products. If you increase the concentration of products, it will shift back to form more reactants. The same thing is true of removal. If you removed a reactant, it would shift back this way. If I removed heat here, it would shift back that way, and so forth. I hope that helped. You're welcome to comment, tell me, Talat, you messed up again. But I'm doing the best I can, okay? You guys stay safe.